We're going to wrap up this chapter with a few more calculations that we can compute for a curve represented by a vector valued function. And the first thing that we're going to cover is curvature. Curvature is the measurement of how sharply a curve bends. So we could say something is very, very curvy, which in that case it would have a very large curvature, or the opposite of curvy would be straight. So if we had a straight line, the curvature would equal 0. For example, we want a numeric way to express the fact that this curve has more curvature at point Q than at point P. So let's say this is our curve, and here's point P, and here's point Q. There's definitely more curving going on here at point Q than there is at point P. At point P, it looks like it's nearly a straight line, and at Q, we at least have a little bit of a curve. So we want a numeric way to be able to express that, and that's what curvature is going to do for us. A figure such as a circle has constant curvature, and that's because the curvature at every single point on the edge of the circle is exactly the same. And the way that I know that is because the numeric value of curvature is inversely related to the radius of the largest circle that can be drawn tangent to a curve at a particular point. So if I wanted to find the largest circle that I could find that draw tangent to point A, it would be this exact circle itself. And it would be the same thing for C and the same thing for B. So if we say that the circle has radius R, the numeric value for curvature is inversely related to that value. So that would mean K is 1 over R. So the larger the circle is, since this is an inverse relationship, the larger the circle is, the smaller the curvature. The smaller the circle, the larger the curvature. So if you imagine at point P, because it's fairly straight at point P, we could draw a really big circle tangent to point P in our first curve. And a really big circle means a small curvature. At point Q, we could fit a much smaller circle tangent to point Q, and since it's a smaller circle, it would have a larger curvature. So this is kind of similar to the curve we had above. And here's our Q, here's our P. If we'd actually wanted to see these circles, and I'm a terrible drawer, we might be able to make it a little bit bigger, but we could see the circle that gets drawn at Q. And if we look at the circle that we would draw at P, just pretend it's a circle. That circle has a much larger radius, which means the curvature is much smaller. The circle at Q is much smaller, has a smaller radius, which means the curvature is much larger. This radius here is always drawn normal to Q. So let's see if we kind of understand this concept. And we are going to try to figure out the curvature, or at least compare the curvature at different points on this graph. We want to order the points on the curve from starting with the one that has the largest curvature and then down to the one that has the smallest curvature. Largest curvature means smallest tangent circle. So if you need to, you can draw a circle at each of these points and compare the size of these circles. That one's really big. That one's even bigger. So I didn't actually intentionally do this, but it looks like the curvature at point A is the largest, and that's because we've got the smallest tangent circle at that point. And then at B, that's our next larger circle, which means the next smaller curvature. At point C, we still have a little bit of curviness there, but not much. The circle is starting to get much, much bigger. And at D, the graph is nearly straight, so we also almost have a curvature of 0, which means we could draw a circle with an infinite radius at that point. So now the actual calculation. If C is a smooth curve given by R of t, then the curvature of C is given by, and we call curvature capital K, and it's not a simple calculation. It takes a few minutes. We've got to find the magnitude of R prime crossed with R double prime and divide that by the magnitude of R prime cubed. Now, this is considered the alternate formula, but it's the one that I think is easier to work with. There is another formula in our textbook, which you're welcome to look up, but I really think this one's the easier one. So let's try a couple of these. Let's use our formula and actually be able to get a number answer back for our curvature. We want to find the curvature of the curve that's represented by R of t equals 3 cosine ti plus 3 sine tj plus tk at the time t equals 5. So we've got to calculate all of this stuff here. So we need R prime and R double prime in order to get started. R prime is going to be negative 3 sine ti plus 3 cosine tj plus 1k. And our second derivative is going to be negative 3 cosine ti plus negative 3 sine tj plus 0k. And then we need to find the cross product of R prime and R double prime. At this point, if you want to, since we specifically said at time 5, your cross product might be easier if you were to go ahead and plug 5 in, but this one actually has a little trick to it. So I'm going to just go ahead with my cross product while I still have variables in there. So remember, with cross product, we're setting up a 3x3 determinant matrix with our components. It just so happens, though, that the components here are functions, but we could still do the cross product. Just means we'll have functions in our answer. So for I, remember, you're going to cross off i's row and i's column and do the 2x2 determinant of what's left over. We get 0 minus negative 3 sine t, which is just 3 sine t for the I. For the j, if you cross off j's row and j's column, you get 0 minus negative 3 cosine t. And remember, when we go to j, we switch the sign, and that determinant was 3 cosine t for the j. For the k, we're going to get 9 sine squared t minus negative 9 cosine squared t, which is really 9 sine squared t plus 9 cosine squared t. If you factor that 9 out, we're left with our Pythagorean identity, and this simplifies down to just a 9 for the k component. So for our numerator, we need the magnitude of this. Magnitude of R prime crossed with R double prime. And notice we still have not plugged t equals 5 in yet. So we're going to square each of our components and add them together under a square root. We're going to get 9 sine squared t plus 9 cosine squared t plus 81. And again, for those first two terms, if you factor the 9 out, sine squared plus cosine squared is just equal to 1. So this comes out as the square root of 90. And that represents our numerator. Magnitude of r prime crossed with r double prime. Now we need the magnitude of r prime, which we cube for our denominator. So for r prime, we're going to go back up here. We're going to have 9 sine squared t plus 9 cosine squared t plus 1 squared is 1. And use Pythagorean identity, and we get that this is just square root 10. That means our curvature is the square root of 90. And don't forget, in the denominator, you're cubing the magnitude of r prime. So this is over the square root of 10 cubed, which comes out to be 3/10, which we can write either as a decimal or a fraction. What that means is, even though we do not have this graph, we have an idea of how curvy the graph is at t equals 5. Also notice we never had to plug in t equals 5 in this problem. So this curve has constant curvature. We got a constant back even though we never plugged a particular time in. And the radius of that circle that we can draw tangent to our curve is 1 over the curvature. So 1 over 3/10 is 10/3, or 3 1/3. So we never had to use the t equals 5 in this problem. And what that means is that we have constant curvature. So let's try another one real quick. We want to find the curvature of the curve represented by r of t equals t minus 2i plus t squared j minus 3k at the time t equals 3. And again, I'm going to hold off with my t equals 3 until the end to see if we really need it. So we've got a few calculations we need to do before we can put together the pieces required for this formula. So r prime of t, the derivative of t minus 2 is just 1i. Derivative of t squared is 2t for the j. And our k component's -3, whose derivative is 0. For our double prime, we have 0i plus 2j, and then again 0k. And we need the cross product of these two vectors. So ijk, 1, 2t, 0, 0, 2, 0. So for our cross product, we're going to get 0i, then 0j, and then 2k. And we just want the magnitude for this, which is going to come out to be 2, because we're just doing 0 squared and 0 squared and 2 squared. So the magnitude of r prime crossed with r double prime is 2. The other piece we need is magnitude of r prime. That gets cubed in the denominator. So we've got the square root of 1 squared plus 2t squared plus 0 squared, which is the square root of 1 plus 4t squared. So curvature is magnitude of the cross product in the top, magnitude of r prime cubed in the bottom. And we do still have a t at the end of our calculation, which means the curvature on this curve is not a constant curvature. It's different based on where you are in time. So we're specifically wanting this at time 3. So now that we have this basic formula, we can plug 3 in for t. And get an answer for specifically what's happening at t equals 3 on this curve. In the denominator, we end up with square root of 37. So if we want an exact answer, this would be 2 divided by 37 square root 37. Or for an approximate answer, we can type that in our calculator, and I get a really tiny number. It's about 9 thousandths. The curvature is about 9 thousandths, so that's a really tiny curvature, which means we can draw a tangent circle that's really, really large in this spot. So 1 over your curvature will give you the radius of your tangent vector, which is about 112.5. So that's a really, really big circle. So we must be at a spot on this curve where we're traveling in nearly a straight line. Because our curvature is so tiny, and if we flip it, the radius of the tangent circle is so large.